before we actually start talking about, well, the KFC theory or the K-femboy cell theory, I thought I'd make a small video about sort of an application of mathematics. And yeah, so for the past few nights, I played a game called Children of a Dead Earth, and I thought it was a very cool game because, well, of course, I'm a nerd. Not only do I like math, I also love engineering. Engineering was pretty much the catalyst for my love for math. It was the reason why I sort of started loving math, and ultimately, it's my goal to be an engineer. So the game doesn't really dabble much into engineering. There is a part wherein you can design, or there is a sandbox mode where you can design your own ship. But in summary, Children of the Dead Earth is a game wherein we basically do space battles, but it's scientifically accurate. Very accurate because it actually incorporates orbital mechanics in it. And so, well, since I thought it was a very cool game, maybe I make a small lecture about what exactly is the science behind it. And why exactly you need to do this and do that, and you can't just, like battle them like in Star Wars, and why spacecraft don't usually have wings. Okay? So let's start with the basics. Why, in Star Wars, you guys see that, or in other space battles, you guys notice that spacecraft, or actually spaceships or battleships, or small fighter aircraft contain wings, right? Now that is kind of applicable in this setting because we can sort of perhaps use space planes in combat and, well, of course, transporting material on and off a planet. But the thing is, in Children of the Dead Earth, spoiler alert, just a spoiler warning, if you haven't played the game and don't know about it yet, I suggest you play it. It's on Steam right now. It's just a couple of bucks. It shouldn't cost you guys much. Or you guys can get a Steam unlock, which I did. Okay, so, yeah, pretty much. So in Children of the Dead Earth, something happened between two gigantic nation states that caused us to evacuate the entirety of Earth. And so we started living in space for a couple of decades, maybe 2 or 3 decades. We spread throughout the solar system, and then, the thing about the game is that it doesn't have things like FTL, faster than light travel, or it doesn't have like really strong lasers or anything like that. It is as scientifically accurate as it can get. It only uses technologies that can exist in the near future, such as nuclear propulsion, I suppose. It even still uses chemical rockets and stuff like that. So you will notice in the game that there is no such thing as fighter aircraft or fighter spacecraft. So you wouldn't see something like like an X-wing in there, or you wouldn't see something like a Millennium Falcon in there. It's mostly cylindrical, cigar-shaped ships with gigantic wing-like structures at the back that aren't really wings. They don't produce lift if they're in an atmosphere. But those are called radiators. So basically, okay, so in this video, I will just talk about the science of the game. And so if you guys like engineering, or if you guys are interested in the game, I suggest you guys keep going in this video, of course. But if you guys don't like spoilers, consider this a spoiler warning. So like what I said a while ago. Okay, so let's start with spacecraft design. So why is it that a majority of spacecraft you see in today's society do not have wings? Well, it's because most of spacecraft are powered by, or they maneuver in space via these things called reaction control systems, or RCS. Reaction control system. And these are small little thrusters on the side of the ship that orient the ship one way or another. So if a ship wants to orient this way, it's going to fire thrusters on this way, upward or downward, to make it such that it starts turning this way. And then, counteract the thrust because it's going to keep moving. The thing about space is that it doesn't have air in it. It's a vacuum. And that's another reason why spacecrafts cannot just battle each other head on. Every move has to be pre-planned. And in fact, a majority of space flight or space travel in today's society or in modern society are powered by computers or planned by computers. So in short, pretty much pilots are useless in space unless they're sort of the people who are monitoring the moves that that the computer has plotted or has done. So if you guys expect a space battle in the future, space battles in the future, near future, or maybe perhaps in today's society, if we were forced to evacuate Earth and we have a war in space, it wouldn't be space battles as glorious as Star Wars, but it would still be a beautiful spectacle. Of course, a horrifying one as well, because war is horrible no matter how you see it. In fact, the game has a lot of political views about how war is perceived, and in fact, it says a lot about how we perceive about war, because we're not the ones in the position of the generals. We are not the ones in position of the president. We are not in the position of the soldiers. We are just civilians, and we do not see the entire nuance of why people fight, of why there is war. In the game, it is stated that excuse me. In the game, it is stated, or it is justified, that the reason why the two most powerful space nation states, the Republic of the Free People and the UST, the reason why they fight is because they want to protect their citizens. Because as long as the enemy or as long as the opponent is alive and their citizens are okay, there will always be a threat to your survival. So it's sort of like dark force deterrence in the three-body problem. So you need to eliminate all possible threats. And as long as there's another part of humanity that aren't on your side, you will never survive, or you can never guarantee the survival of your people. So that's the philosophy of the game. And that's why people fight. Yeah, I know it's still it's a very amoral point of view, but we really can't argue morality if there's a gun put to your head, or if you're dead. We cannot ponder on the philosophy of war if we are dead. So that's sort of the priority, survival first. I understand that this is sort of unfair and things like that, but ultimately the universe does not care if you are moral or not, if you are a Christian or not, if you're Catholic or not, if you adhere to moral values or not. If it's war, and the goal is to win. Well, at least for the game's philosophy, or the game. Okay, going back to the lecture. Okay, so this RCS is one reason why ships in space do not have wings. And that's why in today's society, or in possibly any future space battles, there will be no fighter aircraft. Because there's no air in space, and because there's no air in space, there's no way wings can sort of help maneuver the craft. So you know how aircraft use their wings to sort of roll to the side, they pitch, yaw, roll, using their wings, their elevons. And that's because wings interact with the air around them to produce lift. There's a low pressure area on the top, and then there's a high pressure area in the bottom of the wing, because of the interaction of the wing with the wind or with the air, and then the aircraft lifts into the air. That's the basic principle of how aircraft fly. But there's none of that in space. And so there's no way a spacecraft can maneuver like an aircraft in space, which is why sort of space battles in Star Wars is inaccurate. Because there's no air in space for the wings to sort of make the spacecraft move in a certain direction fast. And another thing in space is that since there is no air in space, your spacecraft has it can accelerate much faster. So you have to really be careful with your engine thrust. So pretty much in space, we don't, me saying that space is absolutely empty is a sort of a misnomer, because there actually is some stuff in space. I believe it's like 0.001% per cubic meter. There's like a bit of hydrogen that sort of travels in space from the sun and from, well, that's what's cosmic radiation after all. So the tiny hydrogen particles traveling near the speed of light that sort of hit us. That's why we need radiation shielding. That's another important thing. That's sort of the thing. That's another reason why your spacecraft cannot be very stylish. Because we need to account for another thing, which is radiation. You guys know about radiation. One of the dangers of space. If you don't shield your crew properly, they're gonna die from radiation poisoning, and they'll get cancer. I mean, 1,000 times the dose of a regular person in their lifetime, just because of being in space. So you have to coat your spacecraft in a thick shield of either running your fuel through the skin, so that's sort of called regenerative cooling, or you can use ablative radiation shielding, which uses a thick material, maybe perhaps such as aluminum or something like that, or metals that reflect radiation or absorb radiation. But they don't last pretty long and are probably weak. And that comes down to the third point of why spacecraft aren't just what they look like in space operas, is redundancy, reliability of spacecraft. There's a reason why spacecraft look more utilitarian rather than stylistic. If we go for a stylistic approach, we lose some redundancy. So if your rocket just looks like, those childish drawings of what rockets look like, it doesn't quite look practical, What we want with rockets and what we want with spacecraft is that they last a long time and they can absorb a lot of damage from enemy fire. So this sort of another reason why it's you may notice that these cigar-shaped ships, the ones that we use in today's society and probably in movies like The Martian, like the Hermes, or maybe in movies such as The Midnight Sky, if I remember correctly, it's the Ether ship. You may notice that these cigar ships are shaped like, cigars, they're cylindrical. And one reason for that, another reason for why it's cylindrical shaped, is that the reasons why they're shaped like cigars is that one, they reflect enemy fire much better. So if your shielding, your ship's shielding is angled sort of like this, or it's curved, if, say, a laser from an enemy cannon, or say a projectile from an enemy cannon fires at you, it has a better chance of ricocheting off rather than directly penetrating the skin. Okay? So it ricochets off if your shielding is curved. And also because notice that spacecraft are pressure vessels. And every time you're circulating air within something, let's say a balloon, air does not love, or pressure does not love sharp edges. That's sort of another reason why tanks, as you see them, like say oxygen tanks in hospitals, or oxygen or fuel tanks in sort of jet fighters or in rockets themselves. There's a reason why not right now.
Hello.
Sorry. Okay. If I'm not gonna get interrupted any further, there's a reason why these guys are cylindrical in nature. Because pressure does not love sharp edges. And that's sort of another reason why if you try to fill a sort of cube with air, it can rupture easily. Because you need to evenly distribute the pressure of your air, or your pressurized material, in a way where it's equally distributed around the shape, or around the volume of the shape or the surface. And so that prevents rupture. And stress, it equally stresses the material on all parts. That's the reason why it's sort of cylindrical in nature. Okay. So alright. So that's the reason why our ships are shaped like cigars and stuff like that. Next, let's talk about the big wing-like structures on the bottom, or various parts of the ships. Now these things are not wings. They are not at all wings. They do not produce lift, and that is absolutely not their function. draw an example of a ship from the game. So the ship is called if I remember, it's called a laser skiff. So you have, if I'm able to draw it properly. Okay, that, and then I believe there's like this, yeah, and then this is where the engines are, and then there are these things here. Oh, and you will notice these kind of things on other spacecraft as well. Now if they have this cross pattern over here, like this, if they have this kind of cross pattern here, these are solar panels. They provide energy for the spacecraft's electrical systems. But if there's something like this, if they're like curved, sort of folded material like this, if they go like this, and if they're sort of curved like this, and then like that, those are radiators. And what are radiators? Well, the thing is, in most deep space probes, you'll notice that they don't quite always contain solar panels. And it's because they're far away from the sun. When you're, say, at planets like Neptune or Uranus, sunlight reaches you at a very, very low likelihood. So you're less likely to receive sunlight in those parts. And well, you need a lot of energy to power the systems of the spacecraft, like say the cannons and the life support systems. So you need a robust energy source, and that would be a nuclear reactor. Well, at least with current technology. Hey,
robust energy source.
Yes. Oh, you guys.
I just heard the word. Robust energy source. Hello.
Yeah, just talking about space battles and stuff.
Yes.
Okay, so we have two options on the table with current technologies. That would be nuclear fusion technology and fission technology. Well, the one that we currently use in today's society is fission technology, wherein we...
Technology!
We have technology.
Technology!
Yes. Okay.
And then battery resistance.
Yeah. Yeah. Okay. So, where was I? Right. Radiators. When you use either of these technologies, either fusion or fission, nuclear reactors.
Shut up!
Technology.
Okay, you guys are actually interrupting.
I'm
this
sorry.
point.
Fusion technology, go.
Yep. And the thing is, when these reactors produce electricity or energy,
They produce
They-
electricity.
yes, of course they do.
Oh my god, how
The
shocking.
thing is, they spew a lot of heat when they produce these energies and electricity. They spew a lot of heat. And we don't want the heat to kill our astronauts.
Astronauts.
You're not funny. So we don't want the heat to kill our astronauts. So that's why these large wing-like structures are here to dissipate the heat. Or to absorb them. I just explicitly said in my video.
I stopped. He's just doing it on his own.
Yeah. Okay. So, of course, we want to put our astronauts as far away from the nuclear reactor as possible, but we still want to make it accessible so that they can maintain it, or well, in case some critical system is affected, they get to fix it easily. And of course, also the engines produce a lot of heat when of course we activate them. So we also want to put radiators there as well. So that's why there's a radiator here near the engine block, because they also produce heat. But heating from engines are also solved by other solutions, such as cooling of the engine. And of course, that's already built into the engine system. We don't need a radiator for the engine to do that. But in general, radiators on spacecraft are used to cool the either nuclear fission reactor or nuclear fusion reactor. Because, of course, they operate at such high temperatures to smash those particles or those molecules together to produce energy. To heat water, spin a turbine, and then subsequently produce electricity for the systems you need to operate your ship. So, that's the reason why we have these wing-like structures that aren't wings at all. Okay. So, now let's talk a little bit about orbital mechanics. Why you can't exactly just engage the enemy. Okay, so you guys know about orbits. Well, not the orbits in the sense of mathematics, but now orbits in the sense of orbital mechanics. So I'm not talking about a group action this time, but I'm talking about an actual thing. So I have a planet here. You cannot just go up. You can't just expect to go up and then, be in space and then stay in space. Because everything that goes up must come down. Basic physics. So instead, if you keep going up, eventually you're just going to come back down. So what spacecraft do, or rockets do to get into space, is that they go up and then go sidewards. And then they maintain that velocity so that they keep falling around the Earth, and not wherein they just end up circling and don't actually fall on Earth or the planet. This is called an orbit. So rockets go up and then sideways, or they just go directly slant, or they go up for a little while and then they slant. Okay? So that's why you see rockets tilt when they launch, because they get into orbit rather than get into space directly. There's no such thing as escape altitude. People keep saying escape altitude. But in fact, what is important is escape velocity, or orbital velocity. For Earth, I believe it's around 3 to 4 kilometers per second, kms, or 3,000 meters per second, approximately. Okay, so once you're in orbit, you have the circular or elliptical orbit. There are two types of orbits here. So the first type is the one that's very unlikely to happen or very hard to attain, which is a circular orbit. Of course, it's governed by the equation x squared plus y squared equals r squared. And, okay, x squared plus y squared equals r squared. And then we have an elliptical orbit, which is governed by the equation x squared over a squared plus y squared over b squared equals 1. And of course, a, b are the 2 points here, I believe. Okay, so there are two components of an orbit. So there's a lowest point and a highest point. You will consider these things as maxima and minima of this function or that function. But if you express this as a function of y and this is a function of y as well, you would call these guys maxima and minima, I believe. And so this part, the highest point, is called the apogee, or the apoapsis. While the lowest point is called the perigee, or the periapsis. And so, okay, from your point here, your planet, up to this point, your perigee, is called your minor axis. Basic general mathematics. This is your minor axis. And then the distance between your apogee and your planet is your major axis. And the little thing to know is that when you're at your perigee, you're essentially at your fastest. Over here, you would get the fastest velocity you can attain in your orbit. While the apogee is your slowest. It could possibly even be 0 at some point around here. A small sliver of t here would be 0. Okay. So another thing that's important, that's sort of key to spacecraft travel, is that, well, no matter what you do, unless you use thrusters or anything or something, your spacecraft will always follow this orbit around the Earth. But the thing is, if you're orbiting around, say, the moon, and you're orbiting between the Earth and the moon, so I'm gonna illustrate here. So this is the Earth, and this is the moon, and then you have some elliptical orbit that sort of goes near Earth. There is gonna be your spacecraft essentially is gonna be subject. Let's say this dot is your spacecraft. It's gonna be subject to the three-body problem now. And you guys probably heard about that. Well, so essentially, well, it's gonna be your orbit is gonna be perturbed by Earth here. But actually, actually, it's more accurate when you're near gas giants because they have higher mass, essentially. So if you're near, say, Jupiter or Saturn, and then you're orbiting one of the moons, in an elliptical ellipse or in, say, a non-perfect circle, your orbit's going to be perturbed, or it's going to be changing at every t. So that's sort of something your computer has to account for. So it's sort of chaotic, but still kind of predictable, because the mass of, we'll say, the gas giants are not precisely as much as the mass of a star. And so these guys don't the moon and the planet do not actually equally attract each other. So it's not entirely subject to the three-body problem, but still, tiny bit, your orbit would be perturbed and would be subject to the three-body problem. Just a tiny bit. Okay, so what more is there to talk about orbital mechanics? Well, you may notice that, well, here, at this point, you're at your fastest. So, okay, let's suppose that you're traveling in this direction in your orbit. You're traveling in this direction. You're traveling this way in your orbit. Later, come on. Let's say you're traveling
I'm just attending your class.
Okay. Okay, so let's say you're traveling in this direction. Your spacecraft's traveling in this direction. And you want to extend your orbit, or if you want to go faster. Okay. So, there are three possible vectors you can change here. The tangent, there is the axial, and then in the third dimension, which I don't think I'll consider right now, is the planar burn.
How plain?
So the planar burn changes the inclination of the orbit. So let's say this is, I can't really express the orbit, I know. But this your orbit is at a 90-degree angle. Your non-planar burn, or if you try to burn it this way or that way, it will change the angle of the orbit with respect to the planet. Now, if you do a tangential burn, it's going to change your velocity with respect to which way you're going. So if you burn your fuel going this way, in the direction of your we'll say your velocity vector, then this part will, or your apogee is going to increase. If you burn at your periapsis or your perigee, well, in the direction of where you're going, your apogee or apoapsis will increase, or its distance, the distance between your perigee and the planet's center will increase, and that means you're going faster. Okay, in the opposite case, if you're at your apogee and you burn, in the direction you're going, right? Or if you burn your engine directly away from the vector going, so say your vector is here, and then you burn going upwards, well, that basically just means that you're losing velocity, and that means your periapsis or your perigee will shrink, and eventually you'll be on a collision course towards your planet, which is not good. To stabilize your orbit, say you have an elliptical orbit and you want to make it a circular orbit. What you want to do is that, say your velocity vector is pointing this way, you want to burn this way also. You want to burn in the direction of your vector directly at your apogee so that it would grow. So in a sense, when you burn here on your tangential, or use your tangential vector, or you alter your tangential vector, this part will also grow and become more circular. So the eccentricity starts to go towards zero, which is, well, of course, a circle, and eccentricity of exactly 1 is perfectly elliptical, which is probably not possible, but still there, theoretically. Okay, now how about the radial burn? Now the radial burn is sort of one of the important ones. Well, these three vectors that you can change are equally important, but the radial burn is something that's sort of done more to conserve your delta V. So, alright, radial burns, they sort of, well, if you go in this way, of course, you still sort of burn velocity, so you would sort of lose this, you would do that, but it would conserve delta V. So these three, manipulation of these three well, a careful manipulation of these three vectors can allow you to evade missiles launched by the enemy. But the thing is in the game, the enemy's missiles can redirect to actually make an intercept course with you. Now, I'm not gonna go in depth on how intercepts work. You basically just want to plan or burn one of these three vectors, or maybe a combination of these three vectors, such that your orbit intersects with another object's orbit, and then at the right time, you catch up with them at that point, or you come to them at that exact point. So that's an intercept. Now, I said something a while ago, which is called delta V. What is delta V? Well, to put it simply, delta V is the amount of change you can make towards your velocity. Other side.
Yan ba hall pass?
Okay. So delta V, or some people use the term dV, or dV. I like to use this big delta. This one here is neat, but they all amount to the same equation, which is the ln of your dry mass over your wet mass W, times your engine's specific impulse times the gravity of the body you're orbiting. So delta V is a measure of how much you can change in your velocity, or how much velocity you can change. So let's say you're at 0 meters per second, and let's say your rocket has 560 meters per second worth of delta V. That means you can change your velocity, or you can only go or speed up to or accelerate to up to 500 and something, what I said a while ago, meters per second. Let's say your meters per second is 3.4 kps, or kilometers per second. That means you can only travel as fast or change as much as 3.4 kilometers per second worth of your velocity. So let's say you're traveling at 3.4 kps, you're orbiting around the Earth, and you want to, let's say you want to make a transfer orbit that sends you all the way to Mars. Well, you would require more than, I believe, more than 4 kps worth of delta V to do that. Unless you use something like a transfer window, which optimizes the distance between the planets to conserve as much delta V as possible. So in space warfare, delta V will be very important. Very, very important, because we don't have infinite fuel. We only have a limited amount of fuel, and thus only a limited amount of delta velocity that we can change. So the ln of your dry mass, so basically the mass of your rocket or your spacecraft without the fuel, that includes already your fuel and your oxidizer, right? Or your nuclear fuel, I'd say, if you're using a nuclear engine like Vasimir or something like that. And you're over your wet mass, which is your rocket or your spacecraft, including the fuel. And just take the natural log of the ratio between these two and multiply that by the engine's specific impulse. Basically, the specific impulse of an engine is how far it can run, or how much time it can run on sort of a quantity of fuel. So let's say for maybe 1 kilogram of fuel, let's say the Raptor engine or a rocket engine can operate as long as 320 seconds. That's a really good ISP. The majority of engines ISP in today's society, chemical engines, are around the range of the 400s. Though some are as low as 30 seconds. So ISP is a measure of your engine's, your miles per gallon sort of thing, or your kilometers per, kilogram fuel, I believe. Yeah. And then G is the gravity, or the gravitational constant of your planet. So for Earth, that's 9.8 meters per second square. So if we do the sort of the dimensional analysis of this, we become the ln of, something m g, right? Some measurement of mass, so probably kg. let's say we measure in kg. So yeah, kg, kg, and then the ln of that. And then so this ISP is measured in seconds, and then times meters per second squared. Okay, and then so we just do the dimensional analysis, and then that's just the ln of that over the times kilograms. And then this seconds here sort of eliminate with this, so this is just the dots times your gravity meters per second square, so meters per second. So kilogram meters per second is your unit measurement for delta V. So yeah, pretty much kilogram meters per second. And that makes sense because we're essentially making our velocity into some quantity, some scalar quantity like fuel, right? We're trying to make it like fuel. So that's essentially the concept of delta V here. We're trying to make what we have, or trying to make a measure of what we have and how it can affect our current velocity. Okay, so what are some of the methods to conserve delta V when you're trying to travel from one planet to the other? Well, one way of conserving it is through using solar sails. So here's a basic gist of solar sails. So every star emits light, and light is travels through space via photons. Now photons don't exactly have mass, but they have something called momentum. So they carry momentum with them, and when they hit an object, they transfer energy to that object. So let's say I have this eraser that's not moving on my hand. Light is currently pushing on it in all directions. Some weak, like here, because it's shaded, but while some strong because it's directly hitting it. So it's sort of pushing it just a little bit, but not enough for us to notice. Okay? So I mean, unlike my hand, I can push it off my finger. I can push it off my hand easily, but light is doing the same thing, but on a very, very, very small scale. So, okay, let's make a gigantic sail, say made of mylar, a conductive material, that captures photons that's emitted by the sun. Okay, so it's like, let's say it's like focusing the sun on a magnifying glass, and then sort of all the light burns something on the ground. That's just essentially what it's like, but instead we're capturing them this time and using them as propulsion, like wind. That's why they're called solar sails. So that's one way to sort of conserve delta V, but I don't think that's used in the game. Now another way of conserving delta V and to get to your location as fast as possible, because with current technologies and near future technologies, travel towards different planets of our solar system would require months worth of travel. So how do we get to other planets faster and with less delta V? Well, one method is via slingshot, or what we call gravity assist. And this is an orbital maneuver wherein, okay, we're not gonna enter precisely into the orbit of a planet, but we're just gonna skim it well enough. We're gonna skim its gravity well, just enough so that it gives us a tiny boost in velocity. And this is a very important thing that's used by either the Parker Solar Probe. It was also used by Voyager, and it was also used by other probes to get to other parts of the planets easily. Now, of course, another way of conserving delta V is via transfer windows. So I believe right now we are currently in a Hohmann transfer window, which lasts around 1 to 4 years, wherein it's the optimal time to launch things towards Mars. So transfer window, of course, it's an optimal time to burn your fuel such that you make an intercept. So, okay, let me erase this. Okay, this is one planet, and then this is another planet. And then we have an orbit around it. Let's say our spacecraft is here, and we want to move here. So, of course, our transfer window is around here. This is our transfer window, because when we burn, well, let's say our vector is going this way. If we burn in this direction, as I said a while ago, this part here will increase or will grow. So if we make it grow enough, we'll make an elliptical orbit that makes a sort of intercept with this object here. Well, that's assuming, of course, it's not moving. But of course, it's having some sort of separate orbit that goes around this planet that we're currently orbiting. So we need to pick an optimal transfer window such that when we burn in that part, we'll be able to intercept it. And of course, once we get here, we're going to shrink our orbit now so that we sort of enter into orbit. So that's called an orbital insertion burn. Okay. So that's one thing that's cool about these things. Okay, so you burn here, going in the direction of your tangent vector, and then you wait, you coast, probably for a couple days, or maybe for months perhaps, if you're traveling between our planets, because space is absurdly big. One astronomical unit is, I believe, like around 3,000 plus or more than that kilometers. Okay, so you coast a bit, and then once you're here, you're pointed in this direction. So your tangent vector is now in this direction. It's not pointed here like this. So what you want to do is burn opposite to that, opposite to your tangent vector, so that your orbit will shrink now, and then so you're inside here. And then you're now orbiting this planet instead of that other planet, or that body. Okay, so how about re-entry? Now, I don't think re-entry is covered in part of the game. We don't really do planetary invasions because that's sort of useless. We can just, instead of invading a planet, just throw rocks at them or throw missiles from them at them in orbit. So really, the essence of space battles or defeating an enemy on an interplanetary scale would really mostly matter only in space and not really on the ground, because invasions are pointless. The enemy can just shoot down your ships as you're going down, and although some of them will make it down, the enormous firepower on that planet will probably crush you. So it would be best to just bombard them or launch bombs or rockets that would hit them, probably nuclear warheads or ICBMs, from orbit. So it's easier. Okay, so another reason why we cannot just engage the enemy head on in combat is because we're constantly moving. We're not just rigid people. So unlike ships, well, ships are sort of moving a little bit, but they're mostly rigid for that matter. They're mostly rigid, and so it's easy for us to fire our cannons at them or our ordnance at them, and then we would expect a good hit. But the thing is, in space, once you fire something, you need to plan it in advance. Because, all right, let me provide an example here. Okay. We're already 40 minutes. Okay. So let's say this is your spacecraft. This is your spaceship. And then this is an enemy spaceship. Triangle. Random shapes. Okay. And you want to fire, let's say, a rocket at them. Say a drone that damages their ship. You want to fire one. And then so, okay. You endow it or give it some velocity going here. It would just keep going that direction unless, well, of course, you program it to correct itself. So, of course, it has rockets on it, so it's gonna sort of burn going here. But the thing is, the enemy is moving and you're moving because you guys are in orbit. You guys are not just, staying in space, because if you just stay in space, you're gonna fall towards the nearest body that has gravity. So you make it go like that, but instead you want to plan it in advance, because at time equals 2, your enemy will be here, right? So what you're gonna do is fire your rocket in advance so that at time 2 or at time 1, right? You fire it, and at time 2, the enemy directly hits it, or it intercepts the enemy. So that's one way. That's the reason why we cannot just keep going, and because we have limited delta V only. We don't have enough delta V to just go straight onto them and then just ram them or shoot them with lasers. We can't just do that. It would be hard. And in space battles, we mostly just launch probes or drones with either maybe cannons or machine guns or whatever, or maybe nuclear warheads in advance, so that they intercept the enemy at one point. So we have to do things in advance. We have to plan in advance and stuff like that in space warfare in real life. So, yeah. Now, believe that's sort of the basic science of it. I can discuss about I'll discuss a little bit about engines, different engine types. I can do that, but that would take up too much time. I'll just say basically there are two main types. There are two main types of propulsion technologies in the game. Well, of course, there are three different types of engines. There's the nuclear, there's the resistojet, and then there is the chemical rockets. The resistojet and the nuclear rockets are basically the same thing. So nuclear rockets or nuclear engines basically take some radioactive isotope, let's say maybe deuterium or perhaps uranium or something like that, or xenon, mostly xenon, and they have this thing called a catalyst inside the combustion chamber of the engine. So you inject your xenon in there, probably maybe in liquid or solid form, and then what it does is it reacts with the catalyst and makes an explosion or combustion that pushes the ship forward. Okay, that's the basic concept of a nuclear rocket. For a combustion rocket now, you have two things. Your fuel and your oxidizer. Okay, so you burn a fire here on Earth, and it keeps burning, of course. And that's because there's oxygen in the air. But the thing is, if you try to burn something in space, like say you light a lighter in space, it's not gonna happen. Nothing's gonna happen. The fuel is just gonna sort of go off. Well, maybe it would sort of spark a little and maybe ignite a little, but it would still die because there is no air in space. There's no oxygen in space. There may be hydrogen in space, but there's no oxygen in space ultimately. Okay, so, but the thing is, if you mix hydrogen together and oxygen and you burn them, there's going to be a big explosion that happens. I believe there's a YouTube short about that. So a guy fills up a balloon with regular oxygen, just what we breathe, and then, pops normally when he puts a fire to it. But as soon as he puts hydrogen and oxygen in it, when the balloon pops or he burns the balloon, it makes a big gigantic explosion that rattles the building. And that's essentially the concept of rockets here. So you have a fuel, and you have an oxidizer, and you direct them into a combustion chamber, and then you burn them, or make them explode, or mostly burn though, and then it produces thrust. The nozzle here directs the thrust in one direction, and most engine shapes are actually like this. So they have the combustion chamber and then they sort of choke it. And that's to amplify the exhaust velocity. So the hot gas that's going down here, the tangent vector at this point, or the tangent vectors at this point, would give us the exhaust velocity. And so, okay, to make the engines more powerful, we run these guys through something called a turbo pump, or pumps. And just like how water is pumped, throughout the building using pumps, we pump these guys to the engine, or make the flow faster and thus the reaction faster, and ultimately make the engine more effective by putting them through pumps. Now, how about cooling? Well, of course, I said a while ago, there are two types of cooling, or two main types of cooling that we use in our engines. There's something called regenerative cooling. Well, this is for chemical rockets, okay? Well, they can also be applied for nuclear rockets, but not much. Mostly ablative type cooling is used for nuclear rockets. Okay, so regenerative cooling is where you have the fuel, right? And part of the fuel that comes from the pump is run throughout the engine and then fed back into the engine. Hey, Kyle. So you have part of your fuel go here and then around the nozzle or up the nozzle so that it cools the engine. And then you feed it back into the engine. Or you can use the oxidizer, but mostly the fuel is subcooled, and then you just inject it there. In fact, this is what SpaceX uses in their Merlin engine. They cool the RP1, or the fuel. RP1 is refined petroleum, and it's rocket grade fuel. And then they run it throughout the engine nozzle and up back into the thing. And then they have some igniter fluid, probably I think T10, that is fed into here that initiates the reaction. And the thing is, to run the pumps, it's not electric, what they do is, well, you have this thing called a pre-burner. So once your engine, produces this kind of thing here, some part of this, actually there's a chamber here that the fuel is put through, and of course also the oxidizer. I can't find the controller, so couldn't find the controller, it's not there. Okay, so part of the fuel is put into this chamber and burned with the oxygen. So this is a small mini combustion chamber that makes the pumps go. And so this stuff is probably just dumped out or put directly into the engine, but that would cause some problem because of soot and some clogging. So that's the basic concept of this is called what's called a regeneratively cooled, partially staged combustion engine, I believe. Yeah. Well, ablative cooling is basically just the engine is made out of a material such that when it burns, right, it sort of chips off a little bit, a tiny bit of material, but in the process it takes away heat with it. So as the materials sort of chip off the engine, you lose heat, and so it doesn't burn out and melt the engine's nozzle. So yeah, that's the basic concepts of this, the space combat in Children from a Dead Earth. And yeah, I know my friends sort of interrupted in the middle of the video. They're a wacky bunch. Though they were funny and, well, good people ultimately. So yeah, this actually, I know this isn't really that much math oriented, but I also want to sort of discuss some aerospace engineering. It's ultimately a very interesting subject for me. I also love making rockets, so making this lecture really helps me relay these important information to you guys. So yeah, that'll be it for this lecture.